CI is always green. No, it was gray a bit ago because I hadn't edited this package in a year because it worked and nobody complained. So I just left it be. Then I wanted the light to be green instead of gray, and so I had to run CI again. And I did. And it passed just in time. Okay, it's 1:30. Yeah, so that's about it. Constant time, discrete random sampling. Any questions? So what is, I'm just going to start out by demoing this because I think that's the best way to show an API. I can create an alias table and I can give it weights like 0.3, 0.6, 0.1. And if I do this, now I've got this alias table object. And that's quite a big printing. And those are printing unsigned integers because this thing represents things internally with unsigned integers, and that's the precise probability distribution. It's hard to represent probability distributions exactly, so we just round to the nearest 2 to the negative 64th, which is typically good enough unless you're running a very long experiment. And now if I sample from this using just, the normal random API, I get a 1, a 2, I should get some more 2s. Oh, a 3, that's unlikely. Not getting very many 2s, Randomness is hard to demonstrate, hard to prove. And I can do like, if I wanted to draw 100 of them, works like that. Just uses the normal random API. So that's all you need to know to use it. And you need to know that it's O of n construction time, which is the time it takes to read the input, and O of 1 output time, which is the time it takes to, you can't beat O of 1. Great. So that's the API. And now, if you want to know more, you can read the docs. The docs tell you more. Shout out to Documenter Vitepress. Okay, so now I want to talk about what the deal is with discrete random sampling and a series of algorithms, and just kind of showing a progression of algorithms. And then I'll dive into exactly the implementation that AliasTables.jl uses, and then we'll have time for questions. So that'll be the rest of the talk. Starting off, looking at this implementation. This is a linear time implementation. It's just a simple loop. You loop over the weights, and the weights need to sum to 1, and describing the algorithm is hard. So like if the random number is 0.5, then as you go through the weights, you first subtract 0.3, and that's not less than 0, and then you subtract 0.6, and that is less than 0, and then you return 2. And if we look at the weights as broken down like so, 1, 2, 3, 0.3, 0.6, 0.1, that r equals rand is like picking a point between here and here. And then the algorithm loops through the buckets and lets you know when you've gotten to the bucket. So based on that intuition, it's correct up to floating point error. Great. Now that's linear time for sampling and linear time for construction. I guess you could call it O of 0 for construction. I don't know. It's pretty quick to construct, but O of n sampling is kind of a bummer. So we can compute the cumulative sum and then do a binary search. That gets us down to log n time, and it's O of n setup. And again, it's picking a random thing, a random point between 0 and 1, and going to the corresponding index. But the algorithm is binary search. I'm not going to go much into this. This is not what AliasTables uses. Okay, AliasTable, O of 1 random sampling, and it's a really simple algorithm. And simple is good because simple is fast. So here we have this accept and alias, and yeah, we're gonna talk about. We're just gonna take for granted what the accept. No, yeah, I'm sorry about that. So I want to start with the sampling method first, and then get into construction, because I'm prioritizing runtime of sampling, so I want sampling to be simple and efficient. And this is not my work. This is, what's his name? Alistair Walker made this in 1977. So nothing new so far. And when we sample here, we're taking a uniformly random index between 1 and 3, and then we're redistributing some of that weight. So to draw a little picture, we start with uniform buckets, because sampling a random uniform number, oh, that's not uniform at all, is fairly easy. Sampling a random number between 1 and 3 uniformly at random, it's O of 1. It's not super fast, but it's pretty good. And then from this, they each have a probability of 1/3, which is wrong, because we want 0.3, 0.6, and 0.1. So we need to redistribute some of this probability. And that's with this, that rand is less than except. Oh, return 0. That's supposed to be return I. Silly goose. Oh, sorry about the confusion there. So if we set all of the accept probabilities to 1, then this is just taking a random number between 1 and 3 and returning it. Pretty straightforward, pretty fast. It's wrong, which is unfortunate. So we need to set some of those accept probabilities below 1 in order to distribute the probabilities properly. So if we start, for example, by looking at this, this 0.1, we want to be distributing only 0.1 here, but we're actually distributing 1/3. So what's 1/3 divided by 0.1? It's about 0.3. That math was not quite right. Anyway, so if we accept only 0.3 of this 1/3, then the total acceptance probability is 1/3 times 0.3 is 0.1, which means there's a rejection probability of 0.7, meaning we have 0.7 times 1/3 probability of going to wherever this alias points to. That's return alias of I. So alias of 2 in this case, let's set that to 2, because 2 probably needs some more bonus points. It wants 0.6 and only has 1/3. So we'll set the alias, this is the accept, and the alias will be 2. Great. And similarly for here, 1/3, we want 1/3, or we want 0.3 probability, and we've got 1/3, so we need to set the alias to 0.9, or the accept to 0.9, and that way we'll be accepting a total of 0.3, and we've got a little bit left over that can go to 2, and then by conservation of probabilities, because we're not destroying probabilities, we're not rejecting ever, we're just redirecting, we know that this is going to add up to, because this is 0.3 and this is 0.1, we've got 0.6 left over here, if we accept 100% of the time. And it doesn't matter what we write for alias. Great. And so I guess the rejection probability here is 0, and the rejection probability here is 0.1. Does this sort of make sense, this alias table sampling? Seeing some nodding, some thumbs up. Great. Great, great, great. So that's, oh yes. One of the big bins to correspond to 2 of the other bins. If you wanted to sample 0.1, 0.1, 0.8, we were asking, like, how do I construct that? If you wanted, well, I'm just going to demonstrate 0.1, 0.1, 0.8. If we did it this way, then, that's a nice 8. Then this would be 0.3. This would be 0.7. And now the probabilities all add up correctly.
No, I mean at the beginning there's a other 0.1 bin, then a 0.8 bin. So the 1/3 bin overlaps with 3 other bins, right?
We have discussion about whether it's possible to represent all probabilities. I have the constructive proof of that later in the talk.
Okay, I'll wait.
Cool. And I'd love it if you interjected during that proof with detailed questions. Actually, let's go to that right now. So next up is a question of how. No, we're going to do one thing first. Performance optimization. Let's say you, let's not optimize to that quite yet. Drawing a random number between 1 and 3, anyone know how to do that off the top of their head? No hands. Anyone know how to draw a random number between 1 and 4? Yeah, we got some hands. The way to do it is you take a 64-bit random number generator, or random number, and you just take the first 2 bits. Very easy. So let's just do between 1 and 4. That seems faster. And we just put a 0 here. And that's a pretty major performance optimization. Just inflate to the next power of 2. So that's an optimization I use in my package. Oh, my timer is turning off. I need to know how long it's been. Oh, great. It's been 11 minutes. So the math is easier here because now we're working with quarters instead of thirds. And now we can talk about how to do a construction. So we start with, this is how much each result wants. And I'm going to switch back to 0.6 and 0.3 because I did that math previously. And this has division and addition and subtraction. I think it might have multiplication too. So that's like, that's a lot. Anyway, so we want, this one needs to give away everything. This one needs to give away some stuff. This one needs a little bit more. And this one needs a lot more. And so what we're going to do is we look at the ones that need to give stuff away and the ones that need to take stuff. And this is an O of n algorithm. It's pretty simple. Actually, very straightforward. You just take an arbitrary one that needs to give something away, and you put it to an arbitrary one that needs to take stuff. So I'll just start with this one, because it'll make the math easier. And I'm going to say, with a rejection probability of 1, or an acceptance probability of 0, we should distribute it to either 1 or 2. Let's do 1, because 1 comes before 2. OK, so now this one is now in the wants to give stuff away camp. Because this one has a probability of 1/2 currently, because it's got its quarter and a quarter from here. And so it needs to give stuff away. And this stuff wants something, and this stuff wants to give something away. And by conservation of probability, we know that they're all going to add up eventually. And so now we can use this one or this one. Either way works. Let's do this one, because we were just talking about it. So it's got 0.25 locked in from here. That can't be given away. Once you're hit with, in the else branch of another bucket, that's a straight return. There's no redirection. So this thing needs 0.05 from its own original bucket, and 0.05 is 1/5 of 0.25. So we'll give an acceptance probability of 0.2, which means we're giving away 0.2 of probability. And we have to give that away to here, because this one doesn't want any more. So we'll give this to 2. Now this has 0.45 allocated towards it, 0.25 originally, plus 0.2. Yeah, plus 0.2 from bucket 1. So it needs a little bit more. This still needs to give something away. And 0.1 is 2/5 of 0.25, So this one will take 0.4 of its acceptance. And we're going with this one because it's the only one that wants to give more of its probability away. And that allocates to 2. And then I'm not going to do the math here. I'm just going to assert that because we're only transferring stuff around, it's got to add up if we keep everything for itself. Now, Jeff, do you have a question? Ah, Jeff says, I think I got it now. Great. Huzzah! So that's the construction algorithm. And there's like little details, but I'm not going to talk about the technical optimization of the construction algorithm because it's less fun to talk about. You can read the source code if you want, or talk to me after, or ask a question. So now let's talk about more optimizations of the sampling function. We've already made that a random number between 1 and a power of 2. There's another key departure from Walker's 1977 and other packages. I don't think any other Julia packages have done this. And that is, what it requires right now is a random integer that we're going to truncate and a random floating point number. And its accuracy is pretty good, but we still have like floating point numbers. Like floating point numbers, this algorithm was written for real numbers. And floating point numbers kind of can represent all the reals, but not quite. And I want it to be perfect, because of course, perfect is good. So let's get, next, I'm just gonna talk about this one. And this algorithm, I just need to see the clock. We reuse the trailing bits. We take a single 64-bit integer, take the first few bits, or I guess it's take the first few bits and allocate those to determining which bucket it'll go to, and take the remainder of the bits and use that in the comparison to the acceptance probability. And when we do that, these acceptance probabilities now need to be unsigned integers. Instead of floating point numbers ranging from 0 to 1, they're unsigned integers ranging from 0 to the acceptance, to 2 to the 64 minus however many bits were being used to allocate, to pick the bucket. And accuracy is a great question to ask here. Like, can we get exactly what we're looking for if we've got unsigned integers in these values instead of real numbers? And the answer is mostly yes. You know how we were allocating probabilities earlier? Those probabilities, when we're allocating them, every time we transfer probabilities, we're transferring them in increments of 2 to the negative 120, 2 to the negative 64. Because if we think about, like, I use the term a pip to represent 2 to the probability of 2 to the negative 64. Each bucket is allocated, in this case, 2 to the 62 pips. And then the acceptance probability is between 0 and 2 to the 62 pips. And so then we're allocating, incrementing this by one bit, adding 1 to this unsigned integer, shifts 1 pip from one to another. And so we can produce any distribution over 2 to the 64 possible outcomes. And that is pretty much the best we can hope for. If we're taking one 64-bit integer, we can that's got 2 to the 64 possibilities, and we can discretely distribute them to any, according to any distribution. And so getting it precise, getting it efficient, that's most of what we're looking for in discrete random sampling. One thing you might be looking for is being able to mutate it in O of 1 time. Might give a talk on that next year, maybe, we'll see. Yeah, and some final, so a final note before we switch to questions, thank you, is this is this like pseudocode, this implementation that I've been talking about in the talk. This is the implementation, the actual package. Let me zoom out. Let me zoom out for a moment. Great. So only a few differences here. First of all, shift is computed based on the length of this vector. So in this case, shift would be 62. If there was more of them, then shift would be more, or less. And then some bit twiddling stuff. I found it faster to store the mask than to construct the mask based on 1 left shifted by shift minus 1 when constructing the mask to mask out before comparing to the acceptance probabilities. Storing acceptance probabilities and aliases together in one continuous chunk of memory, interleaved, so there's only one cache line lookup, is a small optimization. And then some funny business with mod int deleting an error case at inbounds with, it's got its own little proof. I proved it in the source code because, have to use inbounds safely. Didn't include the proof here. And using this silly little construction to store, and this is just like fiddling around until the native code is most efficient. Storing as alias instead of the thing that it'll return, the difference between the thing it'll return and the current value, just results in fewer machine code instructions. So that's a little funny little details. And then there's the API, like plug it into Julia and such, and expose an API if you have your own random source of numbers, like you can just feed in the unsigned integer. And giving variable access to precision, so it could be int64, uint64, uint32, uint whatever. All the little things that go into making a package that actually works. Yeah, so that's the gist of it. And now, let me go on to my next slide of my talk, which is questions. Any questions? Yes, please.
Hi, great talk. When you construct the Alias table, considering you input like a general distribution, there must be some error. Is it possible that the construction function will return like a vector of the error on each bin, so you can make sure that it doesn't exceed some sort of tolerance that you have?
Yeah, so the way construction works, that's a great question, is first we normalize. So if you pass in a vector of unsigned integers, and all those unsigned integers sum to 2 to the 64, then there will be 0 error anywhere. It's just perfect. And if you want me to normalize for you, I can't do that perfectly. If I can do it perfectly, I will do it perfectly. But if I can't, then there will be some slight error. And I worked really hard to minimize that. I think it's like half OLP stuff. I wrote this a while ago. I don't remember the exact details. And you can reconstruct the exact probability distribution of an alias table. We can see here, this display, that's displaying the exact probability distribution. So you can just compare that to your input, and that'll give you the error. Follow-up question from the same brother? Microphone troubles, making sure it's on. Check, check, check.
I meant the other way around. If you input a vector of reals, generalized reals, which might be some sort of weird Julia type number, then I would like a return value that shows the vector of differences of the alias table probabilities to my input, just for future verification if I
yeah, absolutely. So let me demonstrate how that would be done. If we have weights, I'm not going to use custom in float types because I'm not going to precompile a package for that right now. And then I say, oh yeah, that's good. Oh, live coding. So if these are the weights, and then alias table equals this, and then I can say the probabilities Those are the probabilities. And then I can say, I'll divide those by 2 to the 64. And that's the new weights we're getting. And then I can say W2 minus W. And those are the errors, 2 to the negative 20-ish. And it turns out that the weights that we were asking for here are not divisible by, or they don't divide evenly into 2 to the 64. So this is, we got to have some weight error. And 2 to the negative 20 is like, I don't know, what's that? 10 to the negative 20, yes. So it's off by, one of them's off by slightly more than 1 pip, the other are off by slightly less than 1 pip in the opposite direction. So that's, I'd say, the best we can do. That notably, and this is really cool, that is more accurate than float 64. And I use only float 64 and such in the input. So I don't remember what I was doing, but it must have been clever. Yeah, I compute the sum and then I divide and I convert to uint 64. So I'm not going to float 64. And if you give a float 64 input, okay, yeah, you see, float 64 input, I am losing a couple bits at the end. Oh well. Any other questions?
Okay, so yeah, very, very cool. So thank you for introducing, so I never encountered this idea by Walker before. Very, very cool. The way that you demoed it up at the board here, you gave the weight to the very first bucket in need rather than a bucket most in need. I totally agree that this is going to be ON for the construction of this and then ON for the sampling. Is there any potential, could you ever be better off giving to a bucket more in need first so that you'll have fewer overflowing and then needing to flow some more weight back out like happened in this example?
Yeah, that's a very interesting question. Yes, it is possible to make a clever constructor that reduces or minimizes the amount of overflowing. With actual hardware on sampling, the sampling runtime is not affected by the amount of overflow because we're loading the alias anyway, and it's not, this whole sampling function is branchless, and so it doesn't actually save anything. However, it is a great intellectual question, and it is doable, and it's very hard, and I don't do it. And it reduces construction performance. But yeah, that is a clever thing to do. From the audience, it might be a bin packing problem. It's NP complete or something. Yeah, I think it's probably NP complete to minimize, but I don't actually know. I don't remember the specifics. I just remember thinking it was probably not worth it for my use case.
Wonderful. Well, we have time for one more very quick question. Otherwise, seeing no other hands, let's have a round of applause and we'll transition to the next speaker.